All right. In this video, I'm going to cover section 16.2, which is about line integral. So I'm going to introduce a new kind of integral called line integral. But there are two different kinds of line integrals. They are similar, but they are different. The first one of them is line integral of scalar field, scalar valued function. Line integral of small f of xy, namely this is a scalar valued function, or in 3 dimension, we also deal with function of 3 variables, but mainly we deal with this one. And the other kind of line integral is line integral of a vector field. Remember vector field? That's what we covered in the previous video. Either f of xy, that's a vector field on R2, or a vector field on R3. So those are two different line integrals. And in this video, we're going to cover only this one. And in the next video, we'll cover this one. So line integral of a scalar valued function. Scalar valued function f of x, y. So remember, this is called scalar valued function. Or sometimes called a, this is a, so like z is equal to f of xy, a scalar valued function. Namely, the value of the function is scalar. Or sometimes scalar valued function is called scalar field as opposed to vector field. Anyway, it's just a terminology. Then, here's a question. Here's a sort of general question. Given z is equal to f of xy, scalar valued function with 2 inputs, 2 variables, and a curve on xy plane, which is given by a parametric equation of t in R2. So the situation is like this. Here's the xyz space as usual. X, Y, Z. And then suppose you have the surface given by this one, z is equal to f of xy. So this surface is z is equal to f of xy. Then now, you have a curve on xy plane. So xy on xy plane, you have some curve, let's say, like this. And suppose you have like a curve of finite length, and suppose starting point is t is equal to a, and the end point is t is equal to b. At the time a, you are here, and time b, you are here. So you move in this way. Okay. Then now, if you look up to the surface from the curve, you will see something like this. So the corresponding points on the surface at t is equal to a is here, and t is equal to b, you are here. So namely, you get a curve on the surface lying above the curve downstairs on the xy plane. Then now, The question is this. Find the area. So the question is, find the area between the curve and the surface. Namely, this surface, in between the curve and the surface, you will see some surface sort of sticking up from the xy plane like this, right? It's like a wall. And then the question is, find the area of this shaded region. So let's call this curve. So this curve is given by some parametric equation of t. So it's of this form where x component is a function of t and the y component is a function of t. So it's x of t, y of t. So this notation is to emphasize that x is a function of t and y is a function of t. Okay. Then now let's call this curve. C. Let's just give the name. Give a name to the curve. Then now, how should we do this problem? And here's the answer. Answer to this general question. Let's look at what's happening on the xy plane. So on the xy plane, you have the curve. Let's call this starting point A. Let's call ending point B. So we have a, in this case, starting from here, like this, B here. That's how it looks. Then now, let's divide the curve into tiny pieces. And each small portion of the curve is called ds. ds. This is a little displacement in the curve, ds. Then for each ds here, so ds is somewhere around here. This ds. If you look above, you will see a thin rectangle. Oops. Like this. Like this, right? Namely, if you view this picture from this direction, what you see is like this. So this is the axis, and then xy plane is viewed as a line, okay, just parallel to the xy plane. And then down here we have ds here, and then this curve here is here. And what is this? This is part of z is equal to f of xy, but it's a curve. It lies above the parametric curve given this way. So this is actually f of x component is f of t, and the y component is y of t. Okay, that's the curve. So it's parameterized by t. And then if you look above, you will see this thin slice. Okay. All right. Then the area of this slice slice is what? Well, width is ds and the height is precisely the z value of the function. So therefore, the area is height times width. So therefore, the area of the entire region, the area of the entire shaded region is obtained by putting them together. But what do you mean by putting them together? Well, by integrating this thin slice, the area of thin slice, over the curve C. And this is called the line integral of f of x along the curve C. So this one is line integral of f of xy along C. But of course, this itself doesn't tell you how to actually compute it, how to explicitly compute it. And how do we compute it? Well, to compute it, this. We need to express everything in terms of t. Namely, we need to use the parameterization of t is equal to x of t, y of t. And remember, strictly speaking, here, f of xy is actually f of x of t, y of t, because for each xy, we are looking at the part of the surface that lies above the curve, and the curve is given in this way for x components and y components. So therefore, in terms of t, the integrand f of xy is actually a wait a second. F of xy is actually f of x of t, y of t. Need to use this, okay? But we already know that f of xy is, strictly speaking, f of x of t, y of t, y of t. So that's a function of t after all. T. Okay. And then now, what we have to do is to express ds by using t. We need to express ds by using our parameter t. Like how? Like this. So here, if you look at this portion by using a microscope, let me just copy the picture. So t is equal to a here, and t is equal to b times b here. And then this is our ds, this portion. And then now, by looking at, so this length is here. By looking at this by using a microscope, what you see is this. ds is approximated as a line. And then as usual, we write the right triangle, where the increase in x is dx, and the increase in y is dy. So, therefore, by using the Pythagorean theorem, ds is dx squared plus dy squared and square root. But so therefore, ds over dt is written as square root. So you divide this by dt, And divide this by dt, but you have square root, so dt goes inside the square root as a square, so we get this. Square. Okay, so from this, you'll see ds is dx dt squared plus dy dt squared square root times dt. Or another way of writing this is, so x is a function of t, y is a function of t. So that means the derivative is x prime of t squared plus y prime of t squared. You may write it as this. Dt. But what is this? This one is, after all, the same as what? Remember, r of t is x of t, y of t. Let me just write it here. R of t is the vector function where x component is x of t, y component is y of t. So this stuff is, after all, the magnitude of the derivative of r of t, right? Because r of t is this, so the derivative is, remember, the derivative of vector function is just derivative of each component. So you just differentiate each component like this. So this is closing parentheses. Okay, so the upshot is this little thing ds is written as the magnitude of the derivative of the parameterization of t dt. So therefore, by sticking in this ds to here, what we get is this. The line integral over curve C f of x ds is integral of f, but f of xy is, strictly speaking, it's a function of t like this, and then you multiply this. And the t is from a to b. Oops. T is from a to b. And this is the formula for line integral. This is a way to compute a given line integral. This is line integral of f of xy along the curve, given curve C. And then, as a piece of terminology, depending on the textbook, line integral it's sometimes called a path integral. Path integral. Or sometimes it's called contour integral. Just a terminology. And indeed, line integral sounds a little bit strange because line integral is not integral over line, it's over curve. But anyway, just a terminology. And also as a notation, let me just note that this thing here, this is often denoted by this way. So what you do here is basically to plug in x of t, y of t to the given function f of xy, but that is basically the parameterization. So basically what you do is to plug in the parameterization xy to here. For that reason, this expression is often denoted by R of t. So you plug in the parameterization to the function you integrate. So where R of t is x of t, y of t. Anyhow, so let's just work out an example. Evaluate line integral over x ds. So the integrand is just x. F of xy is just x in this case, where C, the curve C is this quarter of the circle, xy, radius 2, circle with radius 2, and then starting from here and then go up to here. That's our curve C. Okay. So how should we do this? Essentially, for line integrals, I would say the key point is, the most important point is to find the right parameterization R of t for the curve you integrate over. Namely, the parameterization is the key. So find out R of t. Then once you find out R of t, everything is in a way mechanical, because all I have to do is just plug into this formula. And depending on the problem, R of t is already given. But like this problem, R of t might not be given. So namely, excuse me. Namely, you have to parameterize this curve C. Namely, you need to parameterize C. But like how? Well, in this case, let me just move it a little bit. This is a part of the circle with radius 2. Part of the circle with radius 2. So there's a sort of canonical way of parameterizing the circle by using the polar coordinates. But polar coordinates with radius 2 in this case. So this is just a 2 cosine t and 2 sine t. Sine t. Then now, so here, since we are looking at only this part of the circle, starting t is 0. That's fine. And the ending t is pi over 2. And so this part, so in this formula, this part is x of t. So x is equal to x of t. That's cosine t. And 2 cosine t. And this is 2 sine t is y. And that's y of t. All right. Then, like I said, to compute line integral, what you have to do is to compute this. Namely, you have to do two things, basically. You have to compute the magnitude of the derivative. So you first compute the derivative and then compute its magnitude. And then you stick in the parameterization to the function you're going to integrate. Let me just write down the formula here. So general formula is this. ds. Okay, this is the general formula is f of r of t, the magnitude of the derivative, dt. So this is the general formula. So first, let's compute the derivative. You differentiate this parameterization. What you have to do is just differentiate term by term. You get the negative 2 sine t and then 2 cosine t. All right. And then from this, you can compute the magnitude as square times square and take the square root. So this is 4 sine squared t plus 4 cosine square t and square root. And that's 2 actually. Root 4, that's 2. Because sine squared plus cosine squared is 1. All right. Then therefore, ds, this little line segment ds becomes here. In this case, 2 times dt. All right. And also, f of r of t. What is this? This means you just stick in here to this. You plug in the parameterization to the function you integrate. Namely, you set x to be x of t. That's in this case 2 cosine t, and then y to be 2 sine t. But you only see x here. So in this case, this is just 2 cosine t. Okay, for this example, f of xy is just x. Maybe I should write this way. Okay, so all we have to do is just to plug in those to here and then compute it. But limits are, I forgot to mention this, from a to b. In this case, a is 0 and b is 2 pi. So therefore, the integral, line integral you want to compute is integral of 2 cosine t times 2 dt. And the limits are from, in this case, from 0 to pi over 2. And that is from 0 to pi over 2 for cosine t dt. And if you work this out, you are supposed to get 4 for your final answer. Okay, so let me just summarize. Basically, in a way, the idea is quite simple. So usually you are given line integral like this, and then what you have to do is to parameterize the curve C. And then once you find out R of t, but depending on the problem, R of t is already given. So in that case, you don't have to do it. And then after that, what you have to do is just compute the derivative and its magnitude, and then stick into this formula. Okay. Then as a last thing for this video, let me mention the scenario for w is equal to f of x, y, z. So line integral of w is equal to f of x, y, z. We can actually easily generalize what we have done to functions of 3 variables. Namely, suppose you, in this case, suppose you are given a curve C in R3 parameterized by R of t is equal to x of t, y of t. So in this case, it's a curve in R3, so you have one more variable, z of t, with a between t and b. Then this line integral is computed as AB. The same formula actually. And then you stick in x of t, y of t, and z of t to the function you want to integrate. And then you multiply the magnitude of the derivative. And that is equal to, so shorthand notation for this is integral from a to b f of of t r prime of t dt. Okay, so this is a line integral in 3-dimensional R3. Then what is this? Well, one sort of physical meaning of the line integral is this. Or one way to use line integral in physics is like this. So C is some curve in R2, or R3 actually. So on the XYZ space, you have some curve, XYZ. You have some curve, like t is equal to a here, and t is equal to b here. And suppose this curve is some kind of wire with some weight. But the weight is not evenly distributed. Okay. But at each point on the wire, we have some density. Let's say f of xyz is a function you want to integrate, but this is the density of the wire per length. Unit is per length. Whatever the unit for length you want to use. So suppose wire is not, the weight of the wire is not evenly distributed. At each point on the wire, at each xyz, you have different weight per length. Oops. All right. And then the line integral is precisely the total weight of the wire. So that's one way to think about a line integral. Anyhow, but the way to compute it is the same. And then there are a lot of exercises you can work on. Okay, so that's the line integral of a scalar valued function, a vector scalar field, so to speak. And in the next video, I'm going to cover a line integral for vector field.